All right, let's get started. Okay, so first off, you all have a present for me, right? Uh, Homework 1. I have a big stack of them right here, so make sure you go ahead and start turning that in now. So homework 1 is due today. Now, I brought this up last time, so I hope everybody has this, right? Right. Just here. So, first off, gotta bring it. Gotta start bringing your manual. Seriously, we are going to start using it on a regular basis. So I'm going to bring it up for a little while, but then after a while, I might not even mention it. So, but just make sure you're bringing it. Okay. So you're turning in your homework 1. Don't forget the technical conference next week, and the scholarship deadline that I mentioned. It's due today. So if you're interested, this is sort of the last chance. Okay. So today, what we're first off, anybody have any questions? Yes, sir.
Yeah, about the technical conference. We got the email today for register for it.
Yes. Yeah. Oh, well, that's like for somebody like me, my first name is actually Gregory, but I'd prefer Greg. That's all that is. So if you have something else you'd like your badge name to be, just type that in. Because they're going to have printed badges, and you can just have whatever you want. Is that okay? Yeah, that's all that was. Because some folks are like some folks go by their middle name and whatnot. So that's all that was. So, but yeah, registration for the conference is free for students. We do ask that if you plan on, like if you're just going to hop in for, to attend a session, like one presentation, I don't know that it's, all that necessary. But if you're going to be there for a while and, you want to do some networking, probably not a bad idea to register just so that all the folks know to have a name badge ready for you. Because if we don't know you're coming, then we won't know to have a name badge ready. What's that? Oh, if you're planning on volunteering, I'd be on campus. I'd actually be here at 7, so that's me. Because people are going to start showing up at 8. So, we're going to need as many hands on deck to direct people for parking and help with registration, setting up the tables and all that. So, but yeah, it's a good way to network and increase employment opportunities. Okay, so far so good? Any questions? All right. Okay, so froze up a little bit. So let's start getting into some stuff regarding tension members. So last time what we did is we sort of discussed some of the various checks that we perform when we assess the capacity of a tension member. And basically what we do is we look at various different conditions, like for instance yielding in the gross section, fracture in the net section, block shear rupture, etc. And we ask ourselves, based on these failure conditions, like say for instance, let's say we're talking about fracture in the net section, we're talking about the phenomenon of fracture occurring right around the connection region. We call that the net section. So we identify that as a potential failure phenomenon, and then we say, well, how do we compute the load that would cause that failure phenomenon? Or when I say failure phenomenon, another way of referring to that is a limit state. So the capacity of that member according to that limit state, if we're talking about net section fracture, would be the tensile stress times the effective net area. So we discussed gross section yielding, we discussed net section fracture, and we discussed block shear rupture. We'll talk about block shear a fair amount later. But the idea is that we're going to, based on these given limit states, determine, well, how much load would it take to fail this element under that given limit state. And if we can appropriately calculate that, we can then start to ask the question, well, if I have a given load, what member must I use in order to safely resist those loads? And that is the design process that we're going to be conducting. All right, so far so good? All right, so we talked about gross section yielding, net section fracture. We talked about block shear rupture. There's also a number of other ways, I guess it's worth mentioning, that a tension member could fail Maybe the tension member is fine, and as you're loading the member, maybe it's not the actual element that fails, maybe it's the connection that fails. Maybe it's the bolts or the welds, or maybe the plate elements right around the connection. We'll talk about bolted connections and welded connections later, but it's definitely something that's worth mentioning. Also, this is a little more, I guess, esoteric, but maybe you've got a tension member in a given system, and it's not the tension member that fails or the connection that fails, but maybe it's some adjacent element that fails that disrupts the load in that tension member as well. So I guess that's something worth mentioning. Also, all this stuff that we're talking about, gross section yielding, net section fracture, et cetera, that's all strength limit state phenomenon, or phenomena. The idea that if I take this member and I load it and I reach that particular load, we're starting to develop the onset of failure, the element failing, not being able to resist further load. That's a strength limit state. A service limit state is intended to ensure that the member performs well on a day-to-day basis, that you can handle it during construction and things like that. So one of the limits that we're going to use is a slenderness limitation, but we'll talk about that later. Right now I want to focus on yielding and fracture. So far so good? Okay. Now, in order to start talking about gross section yielding and net section fracture, the first thing that we need to discuss is gross area and net area. Now, by and large, the concepts are pretty basic, but we do need to have a fair number of examples to ensure that we're able to compute these values appropriately. So first off, in general, when we're talking about gross area and net area, gross area refers to the main body of the member. So if I've got this wide flange section and I've got a bunch of bolts going through the flanges, everybody see that's going through the flanges? Okay. The gross section is just the main body of the member out here. So that's the gross section. The net section is right here around the connection. So if I wanted to calculate net area, in general, the net area equals the gross area minus however much area we're removing out of in this case, out of those flanges due to the presence of bolt holes. Does that make sense? Okay. A couple, just a little bit on terminology. What's it? Yes, sir. Well, let me respond to that in this way. So you're saying there's bolts there as well. Well, when we're assessing tension members, what we're assessing is just the wide flange section itself, just the I-beam, if you will. Now later on, we're going to assess the capacity of those bolts by themselves. So we'll look at, it's sort of looking at it in two separate sides of the equation. What's the capacity of the member and what's the capacity of the bolts? Right now, we're just looking at the member, so that area is gone. Yes, sir?
So, isn't that pretty much just taking the area of the entire chip, no bolt holes, and then subtracting the area of one bolt hole multiplied by however many there are?
You're exactly right. And where you said however many there are, that's going to be the point of some of the examples we talk about later. Because in some instances, it's pretty straightforward. Some cases, not so much. Because if you have a staggered bolted connection, you got to do a little bit of figuring to figure out how many you're actually subtracting. But we'll get to that as we go forward.
You would just calculate the area as if there weren't any bolt holes, and then once you choose your diameter of your bolts, then you calculate the area of one hole multiplied by however many you have.
Exactly. The long and short of that answer is yes, but there's a little more to it, and we'll get to that as we go on. One point I want to make about this before I move forward is if I ever refer to a line of bolts, okay, a line of bolts in terms of terminology is a series of bolts that runs parallel to stress. So in other words, I've got this tension member and I'm yanking on it like so. So these are running along the same direction as the line of stress. Make sense? So this particular member would have two lines of bolts in each flange, 1, 2, and then 1, 2. Make sense? So 2 lines of bolts per flange, and each line has how many bolts? Make sure everybody's paying attention. 5. Okay, there we go. All right. Sound good? So 4 lines of 5 bolts. Okay. Now, let's talk a little bit about the bolt holes themselves, okay? Now, when we calculate the diameter of a bolt hole, the way that we're going to do that is we're going to take the diameter of the bolt and add to it 1/8 of an inch, okay? Now, here's why, okay? So here I've got an image of a bolt, just a circular bolt, okay? The first thing that we're going to do is we're going to add 1/16 of an inch to account for what we call erection tolerance. And the long and short of that is if anybody's ever worked, with their hands, like doing mechanic work, working on engines or maybe working on your car, working on a lawnmower or something like that, if you ever have let's say a 1/2 inch diameter bolt, in order to secure that connection, if you've got a 1/2 inch diameter bolt, the hole that you insert that bolt into has to be a tad larger. You can't have a 1/2 inch diameter bolt and a 1/2 inch diameter hole. You can't get the bolt inside the hole. So you have to drill the hole a little bit larger, okay? Now, for standard structural steel connections, we drill it 1/16 of an inch larger, okay? So the hole is actually physically larger than the bolt by 1/16 of an inch. Now that's 1/16. We also add another 1/16 of an inch to account for what we call damaged material. The idea is, whether you're drilling or sub-punching or using a CNC or something like that, you got to ask yourself, as you're loading this member, you're counting on this connection to transfer load to the rest of the tension member. So what we say is this small little ring of material right around the hole really isn't very effective in transferring stress to the rest of the member. Okay, so we sort of disregard this small little ring of material right here. So we add 1/16 to account for the fact that the hole is physically larger, and another 1/16 of an inch to account for a little bit of damaged material around the drilling. Sound good? So 1/16 plus 1/16 is 1/8. Okay? Everybody okay with this? The hole's physically 1/16 inch larger. Yes, yes. Now, this is one of those points that I mentioned earlier last time when I said one of the things that gets you about steel design is the details. Okay? Right now, because we're assessing tension members, we're looking at the entire member as one cohesive unit. We're asking ourselves how much of this material is effective in transferring load to the entire member. So we use 1/8. But later on, when we actually assess bolted connections, bearing connections and slip critical connections and things like that, when we look at bolted connections, we're actually going to be using the physical diameter of the hole. So right now, we're using 1/8. Later on down the line, when we look at bolted connections, we're going to be using 1/16. So it's just something I want you to keep in the back of your head for later on. Sound good? Okay, it's just one of those details that you'll want to refer to. One other point I'll mention, see right here these green sections of text. I've got section J3.2, page 16.1-120, and et cetera. That's a reference to the pages, in the manual. So if you're wondering where this stuff's coming from, there it is. All right, sound good? Okay. All right, so what we're going to do is we're going to do a couple examples looking at calculating net area. Okay, so let's look at this connection. So first off, we're going to calculate net area of the plate shown. So we're looking at this plate right here, or if you want to look, you can look at this plate right here. So if you notice, I've got this plate. It's being subjected to a tensile load. We're yanking on it. And I've got 8 bolts, right? And the bolts are 3/4 inches in diameter. So I want to calculate the net area of that section. Sound good? Okay. Now, so let me erase this. Oh, there we go. All right. Okay. So example 2A. All right. So if I just look at the member in question, that what is it, 8 by 3/8 inch plate. It probably looks something about like this. I got this, and I'm going to draw what's called a break line. A break line, that's just indicating that that member's going on, you know, forever, I guess, in this direction. And I'm applying an axial load P in, you know, subjecting this member to tension. Now, I've got, what is it, 1, 2, 3, 4, 5, 6, 7, 8 bolts in a grid-like pattern, something like that, right? Now, those bolts are, what were they, 3/4 inch? 3/4 inch diameter bolts. So that little phi symbol in that instance I'm referring to diameter. And this plate is a plate that is 8 inches by 3/8. Okay? Sound good? All right. Now let me ask you this. Okay? In general, what is the formula for net area? It is the gross area minus the area lost due to bolt holes. So if I want to calculate net area, what do you think is the first step? Say it again? Calculate the gross area. So we need to start off by calculating the gross area. All right? So we'll call that AG. So what do you think the gross area is of this plate? Probably pretty easy to figure out. 8 times 3/8. There you go. So okay. So what does that come out to be? 3 what? Nope. There we go. 3 square inches. Simple, right? Now, we need our hole diameter. I'm already making y'all do calculations. Oh my goodness. All right. Now, the bolt diameter is 3/4 of an inch. Okay. So therefore, what is the hole diameter? There we go. Because we take the diameter of bolt. Getting ahead of myself, and we add 1/8 of an inch. So that is 3/4 of an inch plus 1/8 of an inch equals 7/8. Okay. Sound good? Now, let's talk about this. So we're going to ask a couple questions. Let's take it one at a time. Let's see if we can handle this. Okay. First off, when I calculate net area, I'm taking the gross area and I'm subtracting the area lost due to bolt holes. How many bolt holes do you think I need to subtract? 2. All right? Everybody see that? Okay, now if you don't, think about it like this. What's the secret weapon of structural engineering? Samurai sword or a lightsaber if you're a sci-fi fan. When we're calculating these areas, we're calculating cross-sectional areas, right? So if the member is being yanked upon like this, we're talking about cutting a section like so. Okay? So we're cutting a section through 2 bolt holes. Okay? So, to start off, if I want to calculate the net area, so AN, it's going to be the gross area minus 2 bolt holes. So 2, the area due to a hole. Now, before we start calculating that out, let's see if we understand this. All right? So the gross area minus 2 bolt holes. What is the area of a bolt hole? What's the area of a bolt hole? Anybody? Pi d squared over 4, right? Sounds good, right? It's wrong. Okay? Now, here's why. Now watch this. You got to think in terms of cross sections, okay? Think about this. Think about it. There we go. Boom. Think samurai sword or lightsaber through the section. So imagine if I cut this, what am I looking at? I'm looking at an element that looks something like this, right? So I've got a plate that goes on, right? So I've got some bolt holes here, etc. Through that section, it looks like that, right? I know it's a little bigger. This is the area lost due to the bolt hole, right? Make sense? So how do I calculate the area of each of those? I take the diameter of the hole times the thickness. There we go. Does that make sense? It's the first time, it's a circle, pi d squared over 4. Everybody thinks that. But you got to think in terms of cutting a section, right?
What about if you calculate the volume and then subtract the pi d squared? Because at that point you wouldn't be cutting the section, looking at it.
But that's what, but that,
Now we're subtracting a volume.
yeah, but we're talking about cutting sections.
What if you were going to cut the section like a millimeter to the right, and then it's not?
Well, okay. That's a good point, but think about it like this. If you're, that's an interesting point, but think about it like this. If you're taking the member and yanking on it, okay, where is it going to fail? It's going to fail along the path of least resistance. So it's going to fail along the path with the smallest area. Make sense? So if you cut your section, as you're saying, off to the side, that's going to result in a larger area. The plate's not going to want to fail that way. That's an interesting point, but I wanted to address that because that's going to become important later. Yes. All right, hold on. Hold on. Okay, we got distance. Yes.
Two of them, can't you do pi d squared just without the chords, without the 2?
Well,
Since you're doing 2 now.
well, but here, I do see what you're saying, but pi d squared over 4 would be referring to, like, this area, like the area of the circle. We're not looking at the area of the circle. We're looking at the cut through the plate. Right? Does that help you out? All right, and you.
So the cross-sectional area we're looking for is the one perpendicular to the hole.
Exactly, perpendicular through the cut. All right. Does that answer your question? Everybody else okay with that? Yes, sir. It's supposed to be DH. Yeah. Of course, I am a little self-conscious about my handwriting. You had to just point that out in front of everybody. Yeah, I'm kidding. There you go. Exactly. Or 3 lines. 3 lines, not rows. Yeah. All right, so 3 square inches minus 2 times the hole diameter, which is 7/8 of an inch, times the plate thickness, which is 3/8. So what is the net area? Oh, hold on. Now I'm going to ensure that that's an N. Since folks had to point out my handwriting deficiencies. I'm just kidding. So what do we got here? $2.34. That's not bad, right? That's simple. You good?
It's a pretty significant difference.
No, yeah, it can be. Well, if it's this problem, then yeah. We'll have a discussion about that later.
So this would be tension in this way, like if you were yanking it in a different direction, or if you were doing some other force, like a torsional force or something, you wouldn't cut the section that way.
That's a good question. So,
Strategic in which way you cut your section.
yeah, what I'll say is this. These computations that we're performing, these gross and net area computations, are for elements that are subjected to tension. If you have an element that's subjected to torsion or compression or bending or something like that, then the limit states that we're talking about are not even the same thing. Like for instance, things in tension tend to want to fracture, but things in compression tend to want to buckle. So it's a completely different animal. Does that make sense? These computations are primarily for tensile stresses, for yanking on it. Sound good? Everybody else? Okay. Now, that's this one. That's a plate. Let's do another one, okay? So the next one is looking at this. So here I've got a rolled shape. I've got a W10 by 49 that's being yanked on it. Again, 3/4 inch diameter bolts are used, and we're going to go along the same process, okay? So to start, let's go into this. So I've got this. Does everybody have the last one? Everybody have all that? Okay. So we're on example 2B. So similar concept, okay? Now, regardless of what the section is, since you've been through one of these before, I think you can answer this pretty easily. What's the first step in calculating net area? Gross area. So what is the gross area of a W10 by 49? There you go. So let's look it up. So all right, let's leave Siri out of it. Remember, bring your manual. Did you bring yours?
They're very heavy.
All right. And so, yes, the manuals are very heavy, and what I have to say to that is this. So, hold on. All right. 14.4. Okay. All right, hold on. Everybody settle down. 14.4 square inches. All right. For those of you that brought your manual, let's see if did everybody else find that? Okay. All right. First off, okay, that's a good question. Okay, first off, if you're in a colored section, you're in the wrong section. First off, what's that? What's that? One of these. Oh, God. It's going to be one of them days. All right. We're in the first section of the manual. If you go off of the gold tabs, we're going off of DIM, the dimension section of the manual. Okay. Now, Table 1-1 will list the properties associated with W shapes. Okay. Now, if you go to page 1-26, so page 1-26, you're still in the W shapes, and you should start to see here on the left where you see, W12s, W10s, etc. Go to the W10 by 49, and you find an area of 14.4. Okay. Now, is everybody able to find that? Okay. All right. Okay. Now, I'm going to put here Table 1-1, page 1-26. All right.
Is that something you would expect us to do on homework or a test per se?
It probably isn't the worst idea. What I'll say is I'm not going to expect that level of diligence on a test, but I'd say when in doubt, I would report where you're getting values. Plus, it's a good practice to get into when you get out of here. Anytime you start producing calculations, you're going to need to cite where you're getting your data from. My purposes in here are just so that you all know, like I'm putting it up here so you all know where I'm getting the quantities. Sound good? All right. Now, same story with the hole diameters. Okay? So the bolt diameters are 3/4 of an inch. So the hole diameters are 7/8. Now, I'm going to skip writing all that out because we know what's going on. Now, net area, okay? Let me ask you this, okay? How many bolt holes am I subtracting? 4, okay? Does everybody see that? Because I've got 2 lines of bolts in each flange, I've got something that looks like this, so right there along that section, I've got, you know, a bolt here, a bolt here, a bolt here, and a bolt here. So these are what I'm subtracting. So I propose then that for the net area, I have the gross area, and I subtract from that 4 holes, which is the diameter of the hole times the thickness of the flange. What's wrong? What am I missing? The thickness of the flange. So off here to the side, what is the flange thickness? 0.56. Does everybody see that? How'd you find it?
Google.
Oh. Okay. You're pulling up the shape database. Now, if you've got the manual, what value are we not using? You don't have the manual. No, it's 9/16. Okay, let's recall. Why aren't we using the 9/16? Yeah, those are the drafting dimensions, okay? So never use the fractional values in the manual. Always use the decimal values, okay? So we're using the 0.56. So that is the gross area minus 4, 7/8, and then 0.56. So what does the net area equal? 12.44. Bless you. Any questions? Any questions? You good? What? Right now. Okay. Let's talk about some curveballs. Okay? So up until now, if you notice, there's a pattern associated with the connections that we've been doing because they're nice rectangular grid patterns of bolts. And when you cut your section, it's very easy to determine your number of bolts that you're subtracting. It's easy for something like this, okay? So I would say if you want, we can develop sort of a formula for net area as follows. So it's the gross area minus the sum of the diameter of the holes times the thicknesses, right? Bless you. That's I think a fairly reasonable formula, but it only works for grid-like arrangements like this. So what about that, okay? That is not a grid-like arrangement of bolts. That is a staggered connection, okay? We call that a staggered bolt arrangement. Now, the first question that I always like to ask when presenting this is, why do this? You know, why make it more complicated? Why in real life would you ever stagger a bolted connection like this? Why make it more complicated? Well, the answer is really simple, okay? By staggering the connection, what you do is you stagger your failure path. And by doing that, you ultimately increase the net area. Now, if I increase the net area, what's that do to my capacity? Does that make the member stronger or weaker? Stronger, all right? So, you know, if I've got a tight geometry and I can increase my capacity by staggering the connection like this, I'm going to do it, okay? because it doesn't cost any more or less money to drill the holes. You know, like for instance, if you're using something like a CNC, you're just going to program the machine and hit go, and it's just going to go. So it doesn't really cost any more or less money. And if I can increase my capacity and maybe shave some thickness off of that plate, I'm going to do it. Okay. The problem, though, is that it creates multiple failure paths that need to be investigated. Okay. Now, to give you kind of an idea, I've got a connection that looks something like this. One potential failure path would be something like this, just right through that first bolt. Another potential failure path might be something like this. So I fail across those two bolts, but then notice how I've got that one staggered path I've got to deal with. Let me see, I got this one staggered path. Another potential failure path is something like this. And unfortunately, the long and short of it is we kind of just need to go through all of them and see which one is the worst case scenario. Now, one thing I'll point out is this. So if we go back to these failure paths, I've got three of them. I've got, I'll say path 1, path 2, and path 3. Each time I go up a path, I am subtracting one more bolt, right? So this first path, I'm only subtracting one bolt. This one I'm subtracting 2, and this one I'm subtracting 3. Make sense? But with each one of those paths, I add a staggered bolt path, right? Make sense? Those staggered bolt paths, that diagonal failure path, is going to ultimately increase the net area, okay? By adding that diagonal failure path, the net area is going to go up. Now the problem is that if you actually start, going into mechanics and materials and trying to calculate the stresses along a bolted connection where you've got staggered paths, the actual math, the theory that gets behind it is really complicated. It gets really tough. You've got contact stresses and whatnot. It gets a little nuts. We engineers, we have to be able to account for this diagonal failure path, but we need to be able to do it in a reasonable fashion. Now, the way that we account for a diagonal failure path is for every diagonal failure path, we add what's called a stagger factor. Now, a stagger factor, to compute it, it's S squared T over 4G. Now, S is the longitudinal spacing of that diagonal failure path, and G is the transverse spacing. So here I've got an image here on the bottom that's showing a particular staggered connection. So if I'm talking about, let's say, this diagonal failure path right here, okay, so I've got this diagonal failure path. For every diagonal failure path along my staggered connection, I would have to add a stagger factor for this diagonal path. This dimension here is S, and this dimension here is G. Okay? Now, the difference is S goes parallel to the stress, G goes perpendicular. So if I say longitudinal spacing, longitudinal is along the member and ultimately along the stress. G, transverse spacing. G is perpendicular to the stress. All right. Sound good? Everybody okay with that? Okay. Now, all right. This is, I think, sometimes a confusing topic, so everybody will want to pay attention to this. When we look at staggered connections, we always only consider paths that go along what we call the lead line of bolts. In other words, the lead line of bolts is the failure path that leaves all of the bolts intact after failure. So I want you to go through with me on this, and I think you'll kind of see what I'm talking about. So I'll do the first one, and then I'm going to have you all do the rest. So here I've got a plate on a staggered bolted connection, and keep in mind the break line. The break line is indicating that the member's going, all the way out here. Okay, so I'm out here, and I'm acting, like I'm Superman or something, and I'm yanking on the connection. Okay, now I've got this particular path, and I'm asking the question, would this path fall along the lead line? And I propose to you that the answer is yes, because if the plate separates along that line, all the bolts would still remain intact. Does everybody see that? Okay. Now that's this path. Follow along with me. Now you do this one. Would this path fall along the lead line? You tell me, yes or no? Yes, because if I separate, again, the bolts remain intact. Okay? That's this one. Let's do the next one. Would this path fall along the lead line? Yes or no? Yes, because all the bolts remain intact. I propose, would this path fall along the lead line? No, because the front bolt will have sheared off. Okay? We don't consider that section because if we look at the stresses along this section, they're actually less than what's going on, let's say, out here, because this bolt's already picked up some of the load. So it might be a smaller net area, but it's ultimately seeing less load than some of the other sections, so we don't have to consider it. I mean, there are computations that you can do to check it if you want, and by and large, it never governs. So it's really not worth even checking. All right. Sound good? Okay, all right. So I would argue that our final expression for net area looks something like this. We would take the gross area, we would subtract any area lost due to a bolt hole, and then we would add any stagger factor associated with the diagonal path. Okay, and they account for the increased area along that diagonal path. Now that is for bolted connections, and this whole time we've been talking about bolted connections. Well, for welded connections, it's a whole lot easier because if I've got an angle, let's say fillet welded onto a gusset plate and I'm yanking on it, the net area equals the gross area. Because keep in mind, when I compute net area, I'm trying to compute the area that has been removed due to the presence of bolt holes. Well, if it's welded, we didn't remove any material, so it's just equal to the gross area.
So like the bolt never comes with the plate that gets pulled off and stays intact. Like if you pull it and it separates along the line of the bolt, the bolt never goes with the plate.
Are you talking about
Yeah, like right there.
like this?
Yeah, so like the bolt never would go to the left.
No, because the idea is that these bolts are connected onto a plate below it. You know, you're taking member 1 and member 2 and connecting it. And if member 1 fails, member 2 is still there, and it's going to hold all the bolts there. Does that make sense? All right. Yes, sir. And then you.
Is that sound when you actually connect them, that's connected to another plate?
Or something on the other end, yeah.
Well, where that one shears on the lead line, but the other plate wouldn't be in the middle of the plate and not on the lead line?
What?
Like, you see how there's without.
You're talking about on the other member?
Yeah.
The other, well, yeah, that's a possibility, but we're not looking at that other member, we're looking at this one. If we wanted to look at the other member, maybe this is the lead line on the other member, and that is a significant possibility. But the point is this: if you can assess one member associated, you know, assess the staggered connections on one member, you could do the same thing on the other, just flip it and do the same thing. Does that make sense? You sure? All right. I think you, and then you.
Okay, so for the next one where you showed it not going along the lead line, and you said pretty much never have to do those calculations,
Yeah.
what if for some reason the member does fail? Okay, what are the repercussions when you get to those calculations?
What I'm getting at is it would never happen, because I'm saying the math would indicate that wouldn't be the case. That's what I'm getting at.
Okay. So when you have an equal, when you're pulling on that, and it's an equal force,
Well,
I
okay.
don't see how you can have one failure on the top and not on the bottom, because you're pulling at the same, they're both connected on the top and the bottom, and it,
What's
like your plates. So like on like a beam, so on a beam, you're pulling on a beam, okay?
well, you don't pull on beams.
Well, this is, all right, listen. You're pulling on a connection, okay? The bolt goes through both plates.
I kind of get what you're
So if
saying.
you're pulling on them, then
The,
both
you're okay. You're raising an interesting point that we'll talk about later when we look at specifically at bolted connections, because we're going to look at bearing capacities. And what you're referencing is not necessarily a simple calculation, and here's why. Because let's say I'm talking about a bracing connection in a building. So it's like a big truss. So I've got tension members. So I've got this tension member going into a connection. Well, the member might be an angle that's grade 50 or grade 36 steel, but the plate might be grade 50. So sometimes it's not so simple. Which fails first, the really thick grade 36 plate or the really thin grade 50 plate? it's not a simple yes or no question or a binary choice. You have to go through and do the math and check each one. Now, if you got to think about it like this. If you're connecting two equally sized members, yeah, theoretically they would fail at, the same capacity. The point is you're sizing them so that they won't fail. You know what I mean?
I'm just, in my head, looking at it, I don't think that, unless you were bending the connection, I don't think one plate could fail without the failing as well.
Well, yeah, but what we're trying to do is prevent that from happening altogether. I mean, we're calculating the fracture capacity, and we'll say it's 200 kips. We're just going to ensure that that fracture capacity is larger than the loads being applied to it, and then no fractures happen. Like, that's the whole point. But I see what you're saying. Right? Does that kind of make sense? Again, we're trying to prevent that from happening. All right. So far, so good? Okay. Any other questions about this? All right. Now, I want to at least start into this calculation. We're going to look at computing the net area of this plate that's shown, this darker plate. I do want to ask a couple questions so that everybody's aware of what's going on. Now, I've got a particular diagonal path. Let's say it's this one, somewhere right here. Let's say that's a diagonal path. Okay? Help me out. What is the S spacing for that path going to be? 1.5 inches. What is the G spacing going to be? 3.5 inches. Make sense? So what's the thickness going to be? 1 inch. Everybody see that right there? So for each one of those diagonal failure paths, the calculation of a stagger factor is pretty simple, right? Sound good? I actually do want to get some calculations started with this example, and then we'll attack this next time. But has everybody got this? Okay. Okay. Now, so we're on example 3A. Regardless, what's the first step in calculating the net area? Gross area. So what is the gross area?
Well,
12 inches squared. So 12, or getting ahead of myself, is 12 square inches. Okay. All right. So there's that. Let's also discuss the bolt holes. Now, we've got 3/4 inch diameter bolts. So what is the hole diameter going to be? 7/8. So what is the area of a hole going to be? Just a single hole. 7/8 inches squared, because it's the diameter. Here, let me write it out. It's the diameter times the thickness. Oh, I didn't actually do that. So if you want, you can say something like 0.875 inches squared. All right, sound good? Okay. Now, let's also talk about stagger factors. All right, so I'll call that SF for a stagger factor. I would compute that by saying it's S squared T over 4G. All right, and it's a very nice little plug and chug expression. So tell me, what's S? 1.5. All right. What is T? And that's squared over 4 times, and what's G? All right, and what do we got when we plug that out? Anybody? 0.161, is that what you got? And that's square inches, okay? Everybody got that? Okay, now, here's what we're going to do next time. Next time, we're going to identify all of the potential failure paths associated with this connection, and then we're going to continue that on with an example that I think is a little more complicated, but let me sort of explain what happens on this next example. So the next example looks something like this, and it's a funky one, but it's a funky one that you kind of have to think about a little bit. Ultimately, I want to see your ability to assess stagger across different elements of the angle. Now, the long and short of what we're going to do with this connection is we're going to use the samurai sword or the lightsaber in an interesting fashion. Instead of dealing with this angle, which can be kind of complicated to determine your gauge spacings, I'm actually going to cut the angle right here and take this piece of the plate and actually sort of stick it on top right there. So you got the bolt hole right here. And I'm actually going to treat this angle as if it was one big plate, okay? And we'll do something very similar. All right, sound good? All right, again, bring your manual. We will use it, okay? I'm pointing out, I got a number of people here. 1, 2, got a couple folks back here. Got some folks over here. Bring your manual. All right, that's all I got. For those of you that are not going to be in Concrete, y'all have a good weekend. I will see you all on Monday.
Those of us that are in Concrete, we're gonna have a bad weekend.
Of those of you, I'll tell you, have a good weekend in an hour, depending upon what mood I'm in.